So now I've given you the informal kind of intuition behind what makes a subproblem interesting in terms of the knapsack problem. And so now let's write down the math. Let's think about what this stuff looks like abstractly. If you haven't understood the first two videos in this series, you should go and rewatch them. Right? Make sure that you get what's going on when I say remove access to an item, and then either remove or don't remove the associated capacity. Because for the next video, this is all going to be math. Everything's going to be symbolic. We will come back to solving actual instances of the problem using this math, but we need the math first. Okay, so let's write f of I and j. I'm going to define this function, f of I and j, as the optimal value of a knapsack instance that uses items 1 through I and has capacity j. Okay, so here's what this is going to be. This is the optimal value. Okay, so the maximum value of items that you can cram into a subset using items 1 through I using items 1 ... all the way up to I with capacity j. Okay, so the first argument of this is the highest index item that we're allowed to use, and the second argument of this is the actual capacity of the knapsack. Right, so this f of I and j actually specifies the value of a solution to a subproblem of the knapsack. Okay, and so big picture, what we care about, like the thing we're trying to find, is f of n and w. Okay, so our goal algorithmically is find f of n and w. Right? So if I give you an instance of the knapsack problem, what you want is to solve that instance. But what we're going to argue is that you can solve that instance by first solving a certain number of subproblems. And so we're going to introduce this abstract notation to describe kind of the solutions to a subproblem. Okay, so let's also define k of I and j as the subset, as the subset which achieves the above value. Right, so this is defined to be the subset of 1 through I that achieves value f of I and j. F of I and j. Okay, so above in the previous videos, we did this. We said let's think about what f of 3 and 5 would be, right? Where we have items 1 through 3 and a capacity of 5, and we discovered that k of 3 and 5 was actually just the item 3, just item number 3. Okay, so that's essentially what we've got. So what we want to do is we want to write this in terms of subproblems. Okay, so write this essentially as a function of subproblems. So as a function of f of stuff, where that stuff is now smaller than I and j. So write this basically recursively as a function of solutions of subproblems. Okay, so let's think a little bit about the cases that we have here. So case one, yeah, I'll write it as a number, is what happens if the last item, right, so item I, is a member of the optimizing subset, right, is a member of the subset which achieves the value. So I is a member of k of I and j. Okay, so this is the case like our very first case, where our optimal subset was 3 and 4, and 4, right, the highest value that we were allowed, or the highest index that we were allowed access to, was a member of our optimal subset, or our optimizing subset. Okay, so what does this mean? So if I is a member of the optimizing subset, then now I want to use that information to write f of I and j as a function of subproblems. So what I have is that f of I and j can be written as the value of item I, right? Why is that? So this is the first part. It's value of item I plus stuff. But why is the value of item I relevant here? Well, because I've just assumed that I is part of the optimal subset. Okay, so if I is part of the optimal subset, then when I add up all the values in my optimal subset, one of those values will be vi. Okay, so if I is part of the optimal subset, then part of the value of the optimal subset is just the value of I. Okay, and so now I want to write this as f of a subproblem, right? So the optimal value of some subproblem. And let's think back to our example where we removed item 4. Well, if we remove item 4, then what we go to is f of 3 and something, right? So now all we have access to is items 1 through I minus 1. So now if I remove item I, all I have access to now is items 1 through I minus 1. Right? So that'll be my first argument. The first piece of the subproblem says, let's remove access to item I. And then because I was part of our optimal subset, to make sure that we have an optimal subset remaining, we also have to remove its associated capacity. So we'll take the capacity that it was optimal for, subtract off its weight, and then we're done. Okay? So this expression here is a true expression about the optimal values of subsets if I is a member of our optimal subset. Okay, so this is kind of our case 1. Okay, this is one of the ways of recursively defining f of I and j. Right. So what is our case 2? So let me before I write my case 2, let me write some words here that make sure that you've got written in front of you exactly what this is expressing. So we know what this is, right? That's the optimal value of a subset that uses any of the items from 1 to I and has a capacity of j. And so now here, this is the value of I, which is the highest index, right? Not necessarily highest value or highest weight or anything like that. Highest index item that we have available to us. And then this is the value, the optimal value of a subset from items 1 through I minus 1 with capacity j minus wi. Okay, so this is what we're working with here. And so essentially what we've done is we've said let's think about what happens if we remove item I and then also remove its capacity. And that's what this f of I minus 1 j minus wi is doing. Okay, so this is our case 1. Right, case 1 is identical to the first case that we did in the first video, where we thought about what happens if we remove item 4 from an optimal subset. So what's our case 2? Well, our case 2 is that I is not a member of the optimal subset. Right? That's the only other possibility, right? Either I is in the subset or it's not in the subset, right? So now we have we have two case definitions here that cover everything, essentially. And so now, then what do we have? How can we write f of I and j as a function of some subproblem? Well, now it's super easy, right? F of I and j is just equal to f of I minus 1 and j. Okay, what do I mean by this? Well, if I is not a part of the optimal subset, then if I say now you're not allowed to use it, you say, I don't care, I wasn't using it in the first place. Right? That's what this is doing. Is it saying that if I isn't in play, then telling me that I'm not allowed to use it doesn't change the optimal value of the subset. And so basically the idea is, if I isn't in use, then we might as well just ignore it, right? That's what we're saying here. As well, ignore it. All right, so these are the two cases that we'll use to generate an algorithm to solve this thing, kind of along the lines of a DP idea. So to wrap it up, let's look at it like this. So now we know two ways of writing f of I and j. Our goal, big picture, it's not terribly legible, but our goal, big picture, is to find f of n and w, right? So to find this function f of I and j for a particular set of inputs, right, of n and w that define our original problem. We know that f of I and j for every I and j can be written as, this case statement where either it's this or it's this. And so now how can we use this to kind of create an algorithm? Well, we can notice that if I'm trying to figure out which of these cases I'm in, because algorithmically I don't know, right? When I first begin trying to solve this algorithm, I don't know whether I belongs in the optimal subset or not. But what I can do is I can say which of these two values gives me a better number, right? Which of these two values is greater? And whichever one is greater is it tells me the answer. That tells me the optimal subset. So I can write my full expression now combined into just one line for f of I and j like this. So here's my full expression. So f of I and j, and there's going to be one extra case that I didn't mention before, which will just simplify things. But f of I and j can be written like this. So one, it's possible that that item I doesn't even fit in capacity j. So we're going to use that to short circuit some of the further logic. So we're going to say, suppose item I, the highest index here that we're looking at, doesn't even fit in this capacity, then ignore it, right? Then just remove access to it and proceed. So then what we'll say is f of I minus 1 and j. And this case corresponds to the idea that wi, what's the right exact way to write this? Wi is greater than j. So even if there's nothing else there, this item can't fit with this capacity, so we just ignore it. We just throw it away and proceed. Okay? So suppose it does fit. Suppose wi is less than or equal to j. And so there is a feasible subset for this capacity containing I. Well, then what we have is just a combination of the above two ideas. So we have that the optimal value using items 1 through I and capacity j is the larger of these two things. It's the larger of the case where I is not part of the optimal subset, right? Which we know, that's f of I minus 1 and j. That comes from right here. It's the larger of that. And the other one, the other case where I is a part of the optimal subset. So that's vi plus f of I minus 1, comma, and I'll shrink this a bit so that I'm not writing down my face. F of I minus 1 and j minus wi. Okay, and let's fix our formatting just a bit here. So this is, the second line here is quite long, so I'll just extend it out like that. Okay, and there's our full expression, right? And now we can use this to actually construct an algorithm to solve the problem. Like we could use this directly in a recursion with some smart lookups, right? In a recursion where we've actually saved the values of optimal subsets, and you can use this to generate solutions to the problem.